So I started talking about the idea of codes, the idea that multiple kinds of information are often available when you're, for example, talking to a person. For example, you can see the person, so that's visual information. You can hear the person, the sound of a person's voice would be phonological, right, or auditory information, phonological meaning sound. And then also you can try to actually figure out what the person is saying in the sense of what does it mean, which is called a semantic code. Semantic meaning meaning. So these codes may actually be used when we encounter information, and people may actually sometimes use more verbal phonological codes, sometimes more visual codes, sometimes more semantic codes, depending on what they're actually dealing with. So there's some evidence that people use phonological codes. So for example, if you show participants a bunch of letters on the screen to remember, and you look at the mistakes that they make, oftentimes the mistakes they're making are closest to two letters that sound similar rather than two letters that look similar. So for example, if F was in the list that you were supposed to remember and you failed to do so, people were more likely to confuse the F with an S or an X, which sounds similar, rather than with a P, which does not sound similar but looks similar. So in other words, if you're using a phonological code, it makes sense that F and S and X get confused with each other, even though they look quite different from each other. So there's no visual code involved there. But the fact that they often make mistakes where the F was substituted for either an S or an X rather than a P, which looks similar but doesn't sound similar, that suggests that they're actually using phonological coding for this. Now, when you're remembering a phone number too, you actually say it to yourself again and again and again. So that is actually also an example of how people use a phonological code. Can we also find evidence that sometimes they use visual codes? Well, here's an interesting experiment that addresses this, and it's the study that was done in China. And it turns out, I don't know Chinese, maybe some of you guys do, but it turns out that in Chinese, there are particular symbols in the language that are called radicals, and they don't actually have a sound associated with them. So they kind of connect words to each other or something like that, but they don't actually, if you speak Chinese, you wouldn't actually vocalize those sounds. On the other hand, they also have characters that have sound associated with them. So they could be, particular words or whatnot. What was interesting in what they did in this particular task is that they were given participants, Chinese participants, a bunch of those radicals and a bunch of those characters. And then they were basically interested in people could remember these radicals. So the question there is the only way to remember them is through a visual code, because again, there is no phonological code. And the question is, can they actually have any memory for these particular radicals? And it turned out in the results that yes, indeed, even though recall based on visual coding for radicals was worse than characters, which you could code either based on visual or phonological coding. People did better when they had both codes available, but they could do it based on visual coding alone for these radicals. So this suggests that people can actually in their memory system use visual codes as well. Now later on we'll see that there's evidence that people use semantic codes also, but I'll talk about that later. Now making a little jump, and we're going to ask now how people actually access their short-term memory. So one way to test that was actually developed by a psychologist who is still at UPenn by the name of Saul Sternberg, and he developed a memory task where people basically had to scan their memory as quickly as possible to say whether a certain letter was present or not. So here's what happened in that task. People were given a list of letters, and they varied the length of those. So for example, you would get A, N, X, W. And this N here shows that sometimes it was 4 letters, sometimes it was 5 letters, sometimes 10 letters. And then after they were given this list, they then had to watch a monitor, and on the monitor they would present a letter one at a time, and as quickly as possible people had to indicate whether that particular letter was in the set that they were supposed to remember or not. So there's two possibilities here, or at least two. And one of them is that we access memory, short-term memory, in a serial way, meaning one item at a time. The other possibility is that we access it in a parallel way, meaning all the items in short-term memory at the same time. Now, if we come up with predictions about how long it should take people to do this particular task of finding the A, if people do this in a way that's serial, it would mean that, when you see the letter A, you would have to go to the first letter in your list that you're remembering, check if that's it or not. Second letter, check if that's it or not. Then the third letter, check if it's it or not. And the longer your list of letters was, the longer it would take you to say yes or no. Right? So the prediction here, based on a serial model, would be that your reaction time on the y-axis here would increase as the number of items you were comparing it against was also increasing, because you're checking them one by one. The other possibility is that people actually manage to check all of the items in one go. So you see the letter A, doesn't matter whether you have 4 letters in the set you're remembering or 7, you can check all of them in one go, and you're able to actually very quickly respond no matter how many items there were in the word list. So that would be the idea of a parallel access to your short-term memory. Now, turns out that for short-term memory, the data actually looked like this. It actually matched the prediction of a serial model where you check the items off one by one. So the more items you have in short-term memory, the longer it takes you to say yes or no to that particular question. Now, let's be very clear here that there's a limitation to this model, that it has to be just about short-term memory and not long-term memory. And the reason for that is the following. You guys as college students, believe it or not, but they've estimated that the average college student knows about 40,000 words in the English language. Now imagine that I give you a similar task to what Sternberg did, except that I ask you, your whole list that you have is your 40,000 words, and I ask you, hey, is a chair a word? Yes or no? Right? If long-term memory access, to answer that question, was serial in nature, it would mean that you would take every single word you knew, compare chair against it one by one, and only once you've gotten through your whole entire set of every word you know would you be able to say yes or no to that question. If that were the case, the estimate would be that it would take you about 23 or so minutes to answer a simple question like, is chair a word? Clearly that's not the case. So long-term memory is likely parallel in nature. Short-term memory is serial in nature. Now, one issue with that model is, of course, you could ask, well, what does this actually explain? So there's something checking off these items one by one. Well, who is checking this in your head? Is there some little babushka person that, the big guy has a smaller guy in his brain, and that smaller guy is doing the checking for this big guy's brain? Well, that would be an issue, because then the next question would be, well, if that little guy here is in this guy's head, then who's in the little guy's head to check it? Well, you can say, well, there's not a little guy in that little guy's head, and then yet there's not a little guy that's doing it for that little guy's head, and you get into this infinite loop of, something that doesn't actually explain something. That's called the homunculus problem, and it's actually sometimes quite pervasive within psychology, and be aware of it. Sometimes when researchers offer an explanation for some phenomenon or some finding, they actually try to give an explanation that implies some sort of controller that's then controlling the brain. That's really not a very good explanation, because it always leads to the next question. Well, who is controlling the controller? Well, there has to be another controller that's doing that. Well, then who's controlling the controller of the controller? And you see how this becomes very problematic as an actual explanatory type of mechanism. But nonetheless, from these data, we have good evidence that short-term memory is actually serial in nature. You're checking things one by one. Long-term memory is actually parallel in nature.